Jeremy Mould. I'm a professorial fellow in the School of Physics, and it's my pleasure to welcome you to the fifth in our series of July lectures for the International Year of Astronomy, the 400th anniversary of Galileo's telescope. And it's a very large telescope that we're going to be talking about today. It's my pleasure to introduce our speaker, Professor Brian Boyle. Brian did his PhD at the University of Durham, did postdoctoral work at Edinburgh and at Cambridge, and then came out to become the director of the Anglo-Australian Observatory in Sydney. After that, he became the director of the Australia Telescope National Facility in Sydney. And now he has become the director of the Square Kilometre Array, which he's going to be talking to you about this evening. He is a fellow of the Australian Academy of Science, and his scientific interests are quasars and cosmology. Brian.
Well, thank you very much indeed. It's a great pleasure to be here tonight in Melbourne. Tonight I'd like to tell you a little bit about probably one of the largest and most ambitious telescope projects of the 21st century. And that is building a radio telescope 50 times larger than any radio telescope has ever been built before. This, of course, is called the Square Kilometre Array. Now, I'm an astronomer, so I'd like to start with an astronomical number. Okay? This is actually an astronomical number, however, that is actually rooted in a very terrestrial origin. I'm also a physicist, so I have to put units on this particular number. It's 5 million bytes. Okay? That is the amount of information corresponding to the words spoken by humanity. That's throughout all history. When I first, I was actually in a rail, sorry, I'm going to digress occasionally throughout this evening, so please forgive me. I was in a railway carriage, believe it or not, with the Minister for Science, well-known Victorian Senator. And I gave a little fact to him, and his response is, "Oh, Dr. Boyle, surely you're joking. How can you possibly know that number?" Except his response is a little bit shorter and more alliterative than my syllable. Well, I know that number. Well, I can guess that number. Astronomers guess stuff anyway. Because for every person alive today on the planet, there stands 25 ghosts. For that's the number by which the dead outnumber the living. So that means that there have been 150,000 million people that have ever lived on the Earth. By a curious coincidence, the number of stars in our Milky Way galaxy. So there is a star for every man, woman and child that's ever existed on the planet. So you can see how it's going, can't you? 150,000 million people, each person perhaps speaks for about 10 years of their lifetime. A lot of infant mortality very early on, people were eaten by saber-toothed tigers and so on and so forth. And they speak on average around about 100 words an hour. Some people speak more, some people speak a lot more, or less. You can actually get the full number. That's that number I showed you before. Whoops. I've gone a bit too far. 5 million bytes of information, 5 exabytes. Okay? So that's words spoken by humanity. So why am I prattling on about this? It's also actually the information that will be gathered by this new telescope called the Square Kilometre Array. It's the information will be gathered by the Square Kilometre Array in its first week of operation. So you can see we have a telescope 400 and odd years after Galileo, when the SK will finally be operational in the 2020s, that will generate essentially the equivalent of all the words spoken by humanity in a week. Actually, it's very close to the total amount of new information generated in the world each year. That's about 8 exabytes, or 8 million bytes of information. That's going up about 30% per annum. So the thing about the Square Kilometre Array, it's an information gathering telescope in an information age. The big challenge, of course, is to take this information, turn it into knowledge, and eventually, of course, turn it into wisdom. And indeed, this is a lovely little quote. Where is it wisdom that we have lost in knowledge? And where is the knowledge that we have lost in information? Now, when I first heard that, I thought there had to be some guru of the internet age, you know, Steve Jobs or something like that. And of course, I don't need to tell this very erudite audience, this was in fact T.S. Eliot who said this in the 1930s, remarkably prescient. But I believe that the Square Kilometre Array, the world's largest radio telescope of 2020, is really driving our information age. In fact, it's driving the knowledge age, because it's not the information you generate, it's the knowledge that can derive from that information. So, what actual information does radio astronomy provide us with? Radio astronomy, radio waves are a form of electromagnetic radiation, just like optical radiation, that allows us to see different types of things in the universe. Here is a radio image of our nearest star to the Sun. That is Alpha Centauri. Alpha Centauri, the brightest star. No, you're right, there's nothing there. I'm starting to get a wee bit more exciting later on in the evening. Alpha Centauri, the nearest star to our own Sun, very visible to the naked eye, the naked optical eye. 40 million kilometres away. There's going to be lots of millions tonight, I'm afraid. 4.3 light years away. It's never been detected by radio telescopes. Normal stars don't shine in radio waves. So, whereas optical pictures of the sky give us this beautiful picture of the stars in the sky, this is a picture of our Milky Way galaxy. It's a full fisheye lens of the Milky Way galaxy. This is an optical light, you can see the stars. In radio light, you see something quite different. You see the gas, in this case mostly the hydrogen gas from which the stars formed. You can see there's a greater extent of the hydrogen gas. The different colours actually refer to the different speeds of the gas, so we can actually determine the dynamics with these sorts of pictures as well. Up here you can see the Magellanic Clouds in pink, and you can see the bridge between the Magellanic Clouds, the bridge of gas, and the bridges of gas reaching out to them, which gives us some idea of how the Magellanic Clouds, our nearest galactic neighbour Sun, 150 million light years to 250 million light years away from us, have actually interacted with our own Milky Way galaxy and given rise to the stars that form. Other things that we can see in radio waves are pulsars, giving us a view of the universe in extreme physics. Why do I say extreme physics? Well, pulsars are the dead. I've just realised, and I'm very sorry about this, but I've not switched on my microphone. Can anybody hear me? Yeah. Shall I switch it on? Or shall I keep it off? Yes. Off. Oh, I take a vote, actually. I'll put it on and then I can let the audiovisual people deal with my volume. It's actually quite helpful because it allows the simultaneous translation facilities to be used so you can translate my accent into Australian. Where was I? I told you I'd digress. Pulsars. Pulsars are the dead remnants of massive stars. These are little suckers that are about the size of the Earth, the cores of these exploded stars, but they weigh about the mass of the Sun. So that their typical densities are about 500 million grams per cubic centimetre, or if you like, if you took a teaspoonful of the stuff, they'd weigh 5 times the mass of humanity. So they're actually quite dense little beasties. They spin, and because they've collapsed from a big star down, they've actually increased their magnetic fields. And their magnetic fields, like an ice skater, of course, as they pull their hands, they spin faster, the magnetic fields get caught up. And they give rise to this beam of radiation that we see in radio waves. And as this beam of radiation flips past the Earth, we pick it up as a radio pulse. So you can actually, if you turn them into sine waves, you can hear the pulse. Let's see if I can do another one. It's a bit low, isn't it? Let me turn up the volume. Can you hear that? That's the ticking of a pulsar spinning at a few times per second. That's the beam flicking through a radio telescope. And you can go even faster. That's a pulsar spinning a few hundred times every second. So because it's the size of the Earth, the speed of rotation at the equator is about a quarter of the speed of light. So by actually looking at these sorts of radio signals that we get, we can actually look at material that is not only at super dense nuclear densities, but also look at things that are moving close to the speed of light. And in fact, okay, it also gives us a view of other exotic processes. This is a picture just taken in the last 3 weeks with the Australian Telescope Compact Array. This is our nearest galaxy with a supermassive black hole. This is a galaxy called Centaurus A. a few million light years from our own Milky Way galaxy. But this is a galaxy where the pink here is the radio radiation we see from it. And you see this radio radiation stretching over millions of light years from the galaxy. By contrast, the optical image of the galaxy is in the middle. What's actually happening here is this black hole in the middle that weighs about 50 million times the mass of the Sun. It's first of all generating these jets of radiation you can see as these small red worms on the diagram here and here, but also it's causing all this gaseous material to be shocked in the outer regions far beyond the optical galaxy that is giving rise to potentially the birth of new stars. And this just shows you the effects of a black hole, how it can actually extend its effects over millions of light years in the universe. Looking at the optical, we would not get that view. That's not to say radio is any better than the optical, it just provides us with a very different view of the universe. And if our eyes are tuned to radio frequencies, this is the night sky that we'd see. We'd see mostly things that were billions of light years from Earth. Exotic objects and things that went bump in the night and bump during the day as well. So radio astronomy is a very different universe. And of course, I'm going to talk about the tools of radio astronomy. And yes, we use dishes, and yes, we use computers, and we don't always use headphones. I was playing some sounds there, but mostly our data is recorded, of course, on the most impressive and powerful computers that we can manage to get our hands on. Now, when you're designing radio telescopes, there are two facts about radio waves you've got to know. One, that radio waves are large. Typically, radio waves have a wavelength of about somewhere between meters and millimeters. Typically, for a lot of radio observations, about, let's say, 10, 20 centimeters. Okay? And that contrasts with optical, which are about, or less than a micron. So radio waves are typically about 1 million times longer wavelength. Now, there's a simple fact that the ability to see detail in the sky depends on the size of your telescope and also the size of the waves you're looking at. In fact, it's the ratio between the size of the waves you're looking at and the size of your telescope. So if you've got big waves, even if you've got a big telescope, you've actually got a very, very poor resolution. And if a radio telescope, a telescope like the Parkes radio telescope, 64 meters across, were to read that eye chart, it wouldn't get first past E on that eye chart. So actually, the images that you get from single radio telescopes are very fuzzy indeed. Radio waves have also very low energies. Because they're 1 million times, wavelengths are 1 million times longer than optical light, they're also 1 million times more feeble than optical light. And in fact, all the radio energy that's been taken from astronomical sources by all the radio telescopes over the entire history of radio astronomy amounts to the energy of less than 1 snowflake hitting the ground. That's 30 picojoules for the cognoscenti. So, that means there's two very important things that we have to do with radio telescopes. First of all, we need big telescopes. We need big collecting areas to collect up that very feeble energy. This is the largest radio telescope in Australia, the Parkes radio telescope in New South Wales. But even the telescopes that we currently have today on the planet can barely scratch the surface of our radio astronomy universe. We need to build something that's significantly bigger. Biggest telescopes are a few tens of thousands of square meters in collecting area. We need to increase that to a square kilometre or 1 million square meters of collecting area if we're to probe the furthest reaches of the universe with radio waves. The resolution problem is also very important. We just can't keep building telescopes bigger and bigger and bigger. They fall apart under their own weight. And a very clever trick was invented and won the Nobel Prize back in the 50s and 60s in Cambridge, was you can fool the radio waves. Instead of the radio waves thinking the telescope is only as large as a single telescope, you can make the radio waves think that the telescope, from the point of view of seeing detail in the sky, is as wide as a separation between two telescopes. So you can turn the problem that you only have a limited diameter of a telescope for resolution of a few tens of meters out to a few tens of kilometers, or indeed as far as you like, up to thousands of kilometers, This is the very large array in New Mexico, which has what we call baselines, or distances between telescopes, of up to 26 kilometers. So effectively, you change the resolution from being limited by the size of one telescope to the distance between telescopes. So you can change your eye chart from not being able to see, even read E, to actually delivering radio telescopes that have detail that you can see as well as the Hubble Space Telescope. So this is the goal behind the Square Kilometre Array. A radio telescope that's proposed to be built in the next decade. The radio telescope itself would comprise of a number of dishes of the order of 12 meters in diameter, spread over a continent in size. It would also be comprised of some of these flat panels that you see in front of you that would receive radio waves at the very lowest frequencies. It is a global collaboration. Currently, 19 countries are working together on the early development and design of this telescope. And Australia is playing a lead role, not only in the technical development of the telescope, but as one of the potential sites, only 2 sites in the world that could host this new telescope. As I said, it's a continental scale facility. You would have 3,000 antennas distributed over 3,000 kilometres in size. And indeed, now that New Zealand's formally joined with Australia, we can put antennas out in New Zealand to increase the maximum baselines to 5,000 kilometres. Each of these dots represents a farm of antennas comprising about 100 to 200 antennas. These telescopes would be connected together by the world's fastest broadband network. We're talking about moving data between these telescopes at 100 gigabits per second or greater. We're talking about processing the data with this telescope with a machine that's capable of 1 million operations per second, 1 exaflop. Now you might say, well, that sort of computer doesn't exist today. It doesn't. Fastest computers are typically a few petaflops, or a few, almost an order of 3 orders of magnitude slower. But we're building tomorrow's telescope with tomorrow's technology. By 2020, we rely on Moore's law, that is a doubling of processing speed in computers every 18 months, so that when the SKA telescope is rolled out in 2020, there will exist the fastest computer, there will exist an exaflop computer that can process this particular data. So I'm going to show you a little movie of the Square Kilometre Array Telescope. Currently we're in the design phase of this telescope, as I said. The total cost of this telescope, construction cost, the goal is 1.5 billion euros. The operating cost would be of the order of 150,000 euros, sorry, 150 million euros per year. You can see here are the small dishes that the telescope would be comprised of. Here we're looking at the central region of the telescope. The central 5 kilometres by 5 kilometre region of the telescope would comprise about half of the antennas. And as one goes further and further away from that central region, the antennas become more and more widely separated. That is in order to give the best possible fidelity of imaging. Also located in this core region, these central flat panels, which would be sensitive to radio radiation below about a few hundred megahertz. You can see as we pull out from this diagram, you can see the outer stations appearing, and then of course we disappear into blackness, because if you pull any further out, you have to show which country the telescope will be located in, and that's currently still to be decided. So the build would be from 2014 to 2015. I hope I'm not putting anybody off by these fast slews. Cost 1.5 billion, core 5 kilometres, and remote with telescopes, antennas, right out to 3,000 kilometres. And I'm going to stop the thing right here. Okay, so the Square Kilometre Array won't just be doing astronomy. In its very build, it's going to set a number of engineering challenges. First of all, we have to build antennas, these small 12-metre antennas, cheaply. So we have to drive manufacturing technologies and materials technologies. Really, the sensor technology is quite significant as well. We have to develop receiving devices that are state-of-the-art in order to be able to sense these very weak radio waves from the universe. Data transport, this problem of 100 gigabits per second over continental scales. And exaflop computing, building the world's fastest supercomputer in 2020. And another huge challenge, if you're going to be running the world's fastest supercomputer, you have to power this thing. The power issues are huge on the Square Kilometre Array, and looking at renewable energy in order to support this. So essentially the Square Kilometre Array becomes an ICT telescope. The challenge has always been in radio astronomy to try, in the past we've tended to build big engineering structures, concrete and steel, and collect these feeble radiation. More and more of the cost of the radio telescope is now going into the processing end. It's going into the computer at the back end of the radio telescope. So what science is this telescope going to do? The SKA science program is divided into a number of different parts. First one is to look at the dark ages. This is the period in the universe between after the first few 100,000 years, the Big Bang, to about 1 billion years after the Big Bang, where the emergence of the first stars occurred in the universe. It's a region of cosmic time that is actually currently inaccessible to telescopes. With the SKA, we'll be able to probe back to this era. Indeed, there are some preliminary experiments already being conducted, and astronomers here in Melbourne are working on those to look for the first stars as they switch on in the universe, and how they influence the subsequent entire evolution of the universe. We'll be looking at galaxy evolution and cosmology. The Square Kilometre Array will be able to measure the distances to 1 billion galaxies in the universe. Typical galaxy surveys in the past have ranged to a few 100,000 galaxies. With the Square Kilometre Array, we'll be able to do the most sensitive and most detailed map of the heavens ever conducted of the extragalactic universe. With that, we'll be able to do sensitive geometric tests of the distribution of galaxies to help elucidate the nature of this mysterious dark energy component of the universe and dark matter. And we'll also be able to look at the evolution of the universe in gas, complementary to the evolution of the universe that optical astronomers will look at in stars. Just a little view of what the Square Kilometre Array might see. This is the Hubble Deep Field. This is a transformational piece of science that was done in the last century. That's the optical view of the universe. This is actually what the SKA Deep Field would look like in the radio. Well, that's the sort of resolution that you're looking at in the corner there. So it would go even deeper than the Hubble Deep Field for radio astronomy. Tell us about the gas, tell us about the exotic processes at the very edge of the universe. This is only part of the field of the Square Kilometre Array. One of the design principles of this telescope will have a very wide field of view, very panoramic view. To illustrate that, that's the Hubble Deep Field size up there, the optical. Australia is proud to be a member of the Gemini collaboration, an 8-metre diameter optical telescope. That's a view of the Gemini Deep Field, sort of typical widest field you get with optical telescopes. That would be the size of the SKA Deep Field. So many hundreds of times larger than is currently possible with optical telescopes. And this is where your number 5 million bits of information come from. It's because of these huge swathes. We'll be strip mining the universe for radio astronomy data with the Square Kilometre Array. We'll also be doing fundamental tests of gravity, using those pulsars I was talking about, and indeed perhaps even black holes orbiting those pulsars as well, to test physical theories in extreme environments, and indeed using pulsar timing to detect gravity waves as they flow through our galaxy, and we see the oscillations of the pulsars changing of their signals. Even by centimetres, we can take movement of pulsars at the centimetre level from gravity waves. We'll look at cosmic magnetism. Radio astronomy is one of the few ways in which you can look at the magnetic fields of the universe. When I was at Cambridge as a young postdoc, I was given the task of giving lectures, running the seminar series. And occasionally in Cambridge you would get professors who would come and give a seminar that was completely incomprehensible. And of course, as a seminar organizer, you were always the person that had to get up first and ask the question. And the one question you could always ask, for which there was no answer, was, have you included magnetic fields in your study of this particular object? Because nobody ever did, because magnetic fields are a bit of a mystery to astronomers, quite frankly. Radio telescopes are one of the few ways in which you can get a handle on magnetic fields, and with a telescope the size of the SK, we'll be able to probe magnetic fields, not just in our own galaxy, but in distant galaxies, to look at how magnetism, one of the fundamental forces of physics, has shaped the formation of our universe, where there are seed magnetic fields that cause the first stars to collapse, and so on and so forth. Another area of interest is the Cradle of Life. SKA will be able to look at the formation of planetary systems around stars. Not the planets themselves, but the gas disks that form around stars in their very early stages, and watch small planets perhaps generate holes in the gas distribution as they form. And of course, there is always the famous search for extraterrestrial intelligence. This is something that certainly working with my political colleagues, they always wish I wouldn't say, because the search for extraterrestrial intelligence looks like one of these crazy things that one normally does. But the SK is an ideal machine for looking for signals, possibly from extraterrestrial intelligence. The SKA would in effect increase the search radius, or the search volume, for these sorts of emissions by a factor of 100,000. This is the current search radius in red that we use. Some proposed telescopes are just getting off the ground now, will go to there. The SK will give us this search radius for extraterrestrial intelligence. We'll be able to pick up incidental emission from airport radars from around the nearest 1,000 stars. Should, of course, though, the airport radars be transmitting to us. I actually have a theory. I'm going to digress again, I hope you don't mind. I have a theory about this. I shouldn't say this, but I will anyways. I have a theory called mutually assured xenophobia, or the Max's theory, is that if we're sending stuff out to the universe, anybody that can receive that information and do anything with it, i.e. come and visit us, is going to be more advanced than we are. Yep. And the history of humanity has always been bad news when a more advanced civilization meets a less advanced civilization. Yeah? So we as a less advanced civilization will argue that we shouldn't be broadcasting where we are. And every civilization will be thinking that, because every civilization. So no one's going to be broadcasting anything. And in fact, astronomers got into a bit of trouble once. There's the largest current radio telescope on the planet, Arecibo. You may have seen it in James Bond movies. Sent a beam of emission to the nearest stars, well, not the nearest star system, the nearest likely star system at that stage. And they got help to pay, because who gave them the right to speak for Earth? And I quite agree with it. So I'm sorry, all my friends are doing such extraterrestrial intelligence. Good luck to you, but I think no one's going to be broadcasting where they are if they've got any sense of it. Like, it's one of those things. I mean, the chances of it happening, the probability is infinitesimally low, but of course the impact is infinitely high. So how do you work that one out? The overall, of course, is not these science programs necessarily that are important for the SKA. If physics or science tells us anything, it's serendipity that is actually the big outcome of exploring new areas of parameter space. Half of the 5 Nobel Prizes in radio astronomy over the past 50 years, one's in doubt, were due to serendipity. With the SKA, you've got a telescope that's 50 times larger than anything we've ever built before. It will have 100 times the field of view, and it will have 2 to 3 times the instantaneous bandwidth, i.e. bit of the spectrum that you can look at. You multiply those 3 things together, you have a telescope with 10,000 times the discovery potential of anything like it before. So we're going to discover new stuff. I know that sounds like a fishing expedition, but we have all these wonderful programs that we've set up, and it's going to be something. The universe is not only queerer than we imagine, it's queerer than we can imagine. Okay, I'd like to tell you a little bit about Australia's particular role in this telescope. And it really starts with a bit of physics, actually. We live in an expanding universe, and radio astronomy, a lot of the stuff that we're looking at, the gas, is actually hydrogen gas. It's the most common element in the universe. And a brilliant piece of work in the 1950s, people predicted that you would see hydrogen at a frequency of 1.4 gigahertz, or a wavelength of 21 centimeters. And this is because a hydrogen atom has one proton and one electron. They both have spins, quantum mechanical spins, and every so often the spins, the electron spin goes opposite to the proton spin in the middle. Every so often it happens about once every 11 million years. But there's enough hydrogen atoms out there to actually make it a detectable signal. In radio astronomy, when they first picked this up, hydrogen, we protected that part of the spectrum. 1.4 gigahertz, there's a lot of other people who want to use that part of the radio spectrum, broadcasters and so on and so forth. But that was actually protected, so that you couldn't broadcast in that particular frequency. So radio astronomers are very happy studying hydrogen. The only problem is, as you build a bigger radio telescope, you can look further out into the universe. And what happens when you look further out into the universe? The universe is expanding, and that wavelength of light, that started at 21 centimeters of 1.4 gigahertz, gets stretched. And it gets stretched to longer and longer wavelengths, or lower and lower frequencies. And I see a few people nodding, because yes, you go through the mobile phone band, you go through the aircraft band, digital TV, and you end up in the FM band for radio astronomy. And it's a cruel twist of fate that the first stars in the universe will be shining in hydrogen about the frequency of Mix 101. Who knows, you may have heard them already. Well, if you listen to Mix 101, isn't it? And that is why. Now, of course, so what you want to do, now remember that snowflake? I mean, what chance have you got of seeing snowflakes in the blizzard of Mix 101 FM? So you have to protect these bands. But do you think you've got any chance of protecting those bands and stop broadcasting? It's not going to happen. So what you have to do is to go to a very special place on Earth where there is no radio frequency. No radio frequency from just FM broadcasters and digital TV broadcasters. It's every generator, not biologically, you don't generate radio waves. You drive your cars and so on and so forth. Everything mechanical will generate radio interference. And that's why there are two places in the world where the conditions are just right in order to conduct an experiment of this scale and this sensitivity in a crowded radio spectrum. Now, I know you could go to Antarctica, but frankly, trying to put radio telescopes at -70 is a little bit of a challenge. And laying a 100 gigabits per second broadband network over 3,000 kilometers of Antarctica, well, there are things I'd rather not do. So there are two countries that have been shortlisted for the site for the international SKA program. And that is Australia, and this week or next week, Australia and New Zealand will formally sign an agreement between our respective ministers for New Zealand to join Australia's bid, and Southern Africa. In one case, the core in Australia is located in Western Australia, here. And in the other case, it's located in the Karoo region of South Africa. Well, tonight I'd like to just focus on Australia, so let's get rid of Southern Africa, if it were only that easy. I didn't say that. I thought I'd give you a little blow-up of the region that we're going to be placing, or we're planning, or we're advocating that probably one of the world's largest scientific experiments should go. And this is the Geraldton region of Western Australia, or more precisely, the Midwest region, just west of Geraldton. And even more precisely, this is the Murchison Radio Observatory Astronomy, potential home for the world's most ambitious scientific project of the 21st century. It's in the Shire of Murchison. It's a wonderful shire. They're very proud that it's the only shire in Australia with no towns. It has a population of 110. Actually, it is going down a little bit because the previous census, the population was up to 160. I think those 50 undecided voted with their feet. Just for scale, and my European colleagues love this one, that's the Netherlands beside us. You give a talk in Europe, and people realise the Netherlands, population of the Netherlands is about 30 million, the same area as 110. We are talking in some seriously empty part of the world. This bullseye target, this shows you a little bit about the region. This is the Murchison Radio Astronomy Observatory. CSR have just purchased the lease of the actual pastoral lease for the whole property. That's 385,000 hectares. CSR has increased the size of its property holding in area by a factor of 100 in one fell swoop. The central area where the telescope, the core of the telescope will be located, and we're actually excised from the pastoral lease, is 127 square kilometres. Around it, we've placed several regions. These are what's called radio quiet coordination zone regions. We're working with the Australian Communications and Media Authority to place radio quietness. So even though this is one of the unique places in the world, we'd like to keep it that way, and we've actually put legislation around it so we can protect the area from broadcasts. And you can see the size of this. The size of this area is larger than Washington State that we've now got broadcast control over. We're just about to go out with a tender for a fibre optic link from the site to Geraldton. That's 315 kilometres. The National Broadband Network just 2 weeks ago announced one of the first black spot routes because of the SKA was between Geraldton and Perth. And we have already a 1 gigabit per second link going from Perth out to the rest of the world. So we're already building the skeletal bones of this particular broadband network that we need to do. Going right up now, this is actually the central area of the Murchison Radio Observatory. It's not Mars. To give you some scale, that little dot there, that's our radio frequency monitoring caravan out at the site. That is actually sort of at ground zero, if you like. It's a little breakaway, about 30 metres in diameter. And the population out here is 3 nanohumans per square metre. SI units, 20 micrograms. It's a unique place. It's a wonderful place. There's a little bit more kit out there. This is the sort of flying into it, so you get some idea of the relief. There's not much relief. I mean, relief in terms of height. There's not relief anyway. Now, one of the things that we're planning to do at this site, in order to demonstrate just how good it is, and we know it's pretty spectacular, is to build the world's most advanced survey radio telescope in advance of the SKA on this site. This will be the Australian SKA Pathfinder telescope. The government will provide us with $110 million to build 36 antennas, each of which will be 15 metres in diameter. It will be the world's leading survey radio telescope. In the first 6 hours of operation, it will generate more data than currently consists of all the world's radio astronomy archives. It's going to be an international collaboration. We've already put out a call for interest in this particular telescope. We've received proposals that would, if we didn't do any whittling down, take 25 years to observe with this telescope from over 600 people around the world, 19 countries. It is designed to demonstrate the quality of the Australian site. So 36 12-metre dishes. Can I tell them a story about the dishes, Rachel? These dishes, we've actually, we're contracted these dishes from China. There's an organisation called Sexy 54 in China that are building these dishes at a remarkable price, less than $300,000 per dish. But you can imagine contracting with a Chinese company has given us a few problems with our local manufacturers. And every so often we get stories in the press about these antennas. The most recent one was that the Chinese had installed spyware on these telescopes. So when we put them out on the site, and the first telescope will go out on site on November of this year, that it was going to be listening in to the local, it was 400 kilometres away, US airbase just north of Geraldton. So that gave me an interesting morning or two trying to respond to that particular stuff. But it's remarkable because China is also one of our collaborators in the International SK program, and the opportunity for the Chinese manufacturing industry to build the antennas has really brought in China. We want to be a major partner in this in a very interesting, a very dynamic way. We're also going to be building it with an innovative radio camera design. And this is going to be the heart of this wide field of panoramic view technology. The we hope Australian ideas are actually going to go straight into the SK design overall. And it's going to be built at the Murchison Radio Observatory, we get our first antenna on site in November, December of this year. We'll have 6 antennas on site and start doing our first science by the end of next year. And by the end of 2012, we'll be fully up and running, ready essentially for the SK to be built around it in the years beyond. And now for the rest of the talk, I'm going to go through this system engineering diagram in a little bit. Okay, so how do you build a radio telescope? You have an antenna to collect the data. You have what we call a feed, which is essentially the detecting element. In optical astronomy, it's a CCD, little camera. In radio astronomy, up to recently, it's been a single horn. You have a radio telescope. It's not quite right. You can think of it as a single pixel camera. What we want to build is actually a multi-pixel camera for radio astronomy. So you're not just looking at 1 pixel in the sky, but you're looking at up to 100 pixels on the sky. So you're increasing the field of view by a factor of 100. Those signals from that detector are amplified up. They're amplified up by a factor of 1 billion in order to give measurable signals, turned into digital data. They're processed at the telescope, and then you have a lot of fiber, and you take all the processed data from all the different antennas into what we call a correlator that combines all the data together to produce your image. So this is your sort of imager, and then of course you have to power the whole damn lot. The correlator is going to be a bit of a challenge. As I said before, this is what we refer to as climbing Mount Exaflop. A little bit about this diagram. This is a function, along the bottom axis here I've got time. And up this axis I've got flops, or floating point operations per second. If you look at the red dots, this is actually the fastest computer in the world. Okay? So at the moment in 2000, this diagram is 6 months old, in 2008 fastest computer was about a petaflop. In order to get to the full SK, it has to be an exaflop. We're off the top of this diagram. But if you extrapolate that line, you see how it moves up to the full SK, an exaflop in 2020 will be deliverable. In radio astronomy, we're currently down here. With ASCAP, the Australian SK Pathfinder, we have to deliver the world's 50th fastest computer. But we also have, in terms of the first starting to build the SK, we have to be very close to this line with the first world's fastest computer. So we're working with companies like IBM and Cradle, because they love this. This is a challenge for them. And they see this as a fantastically exciting project. IBM, senior executives or senior engineers meet every 2 weeks to discuss what's going on in the SK. That's a tremendously humbling experience. We've also got to deliver the telescope with a reasonable energy footprint, at least a non-carbon footprint. This is the sorts of power requirements as the SK would be rolled out. ASCAP would require a megawatt. If I was just, of course the Murchison Radio Observatory, won't surprise you know, is not on the grid. And even if it were, a megawatt is quite a sizable power bill. It's a very sizable diesel power bill, not only in cost, even at current rates it's $4 million per annum, but in carbon footprint it's horrific. So we're actually factoring into this the building of a green energy, a renewable energy component to our power station. And it will be solar thermal power. We've looked at a number of things. We're also trying to reduce the power footprint, and we're experimenting with geothermal cooling of the telescope. You drill holes into the ground about 30 meters deep, and you use water to keep the ground temperature nice and cool. You pump that water around to actually cool the telescope and reduce your power bill significantly. So that's one way forward on this. But the full SPA is going to be requiring 100 megawatts of power at its central site. Other sites will have the order of a megawatt. Again, it has to be renewable energy. and again, another area that we're working with power companies in order to deliver this. If we can deliver a sustainable, off-grid, robust, green energy power solution that will work 24/7, radio telescopes work around the clock, that sort of system will also be essentially the gold standard for what Australia would require in off-grid towns as well. The sort of scales that we're talking about with the SK easily power small towns. This is this radio camera. I'd like to introduce you to this chap who's one of my heroes. This is a chap called John O'Sullivan. In 1996, he was the lead author on a patent for a little thing called wireless local area network technology. So he invented the wireless LAN standard 802.11a and G standards that currently sit in most people's laptops. He invented that actually a long time ago. It dates back because John was a radio astronomer, and he was given a task of looking for black holes in radio astronomy data, and that's the start of when wireless LAN, that was the beginnings of wireless LAN development. So it just shows you that from very esoteric beginnings, the whole wireless LAN story emerged. Now, of course, it wasn't entirely due to radio astronomy. The whole Australian innovation area was responsible. But John has now come back to work with us on the phased array feed camera because he thinks that the challenges that we are setting him and we're setting our engineers in building this are amongst the most stimulating challenges anywhere that he's come across so far. So this is going to be our radio camera. Here it's at the focus of a test-bed telescope that we have out in the parks, Radio Astronomy Observatory. Just to give you an idea of how it changes our view of the universe, this is what ASCAP, the Australian SK Pathfinder, the field of view would look like without a radio camera, like this is just a single pixel. And this is the field of view that we'll get with this radio camera. So essentially, making the universe panoramic for radio astronomers. Our optical brethren have been having this advantage for many years. Now we're going to redress that particular balance. So, I hope I've given you some idea of the challenges and the excitement in the Square Kilometre Array. Frankly, if the only thing that the Square Kilometre won was a Nobel Prize, I'd be disappointed. Because in the same way that Galileo changed our view, society's view of the universe, I'd like to think that big, imaginative projects like this also change our view of the universe. And that the benefits are much beyond that of astronomy. If we look at things like the Large Hadron Collider, for example, I know looking for the Higgs boson is exciting, but of course we shouldn't forget that the technology development behind the Large Hadron Collider also, of course, led to the web and changed our society's whole societal view. I'm not saying the SK will give rise to a new web, but it is a technology challenge of the same order of magnitude as things like the Large Hadron Collider. So I'm very privileged, I'm very lucky to be working with some of the best people in the world to deliver this telescope, and I'm also very excited that I think Australia is in the pole position for hosting the most exciting and challenging project of the 21st century science. Thank you very much.
Fascinating look at Australia's answer to the Large Hadron Collider, and I wonder if there are any questions. Yes, over there.
Square Kilometre Array, but a core of 5 by 5 and a baseline of 3,000.
Yes.
So why is it called the Square Kilometre Array?
There's a total collecting area. If you add all those, there's about 3,000 dishes, 3,000 10-metre diameter dishes. 10-metre diameter is roughly about 300 square metres. 3,000 times 300 square metres is a square kilometre. So it's a square kilometre collecting area, but not on the ground, not all in one lot.
Thank you.
Take your pick.
Oh, I don't know. I think you had your hand up there.
With such an increase in field of view, is there any chance you're going to lose sight of the trees, the forests? Sort of?
Look, it's a really good question. A lot of people have asked that. And I think a lot of other data schemas across science, biology and so on, a lot of people say, wait, do you have enough postdocs even to look at this particular data? So yes, it is a real challenge. I'm really thinking how hard to, I mean, it's such a good question. I don't have a good, of course you may lose some of the information. I think I focused on wide field of view. I think there's also another important area. We can also split up the data, not only across the sky, but split it up in time. And looking at variations in the temporal domain, I think is another tremendously exciting area. I think we simply have to develop the software tools and techniques in order to be able to pull this information out from this vast quantities of data. And of course, there are many people who are working with similar problems in different disciplines. You know, it's looking for the small trends in climate data with the massive data sets that we have. And it's not just in the observational, it's in the theoretical area. People are doing very comprehensive simulations in the climate space, in the water space, and trying to pull small signals from vast quantities of data. So yes, there is going to be an issue. There's going to be an issue with getting a number of people in order to be able to analyze this data. But I think it's such a leap forward that we're going to certainly very quickly discover the low-hanging fruit in this, and there will be lots of low-hanging fruit.
There's a pension question 2/3 of the way back there.
Can I ask a question about the 100 megawatts? 100 megawatts is a huge amount of electrical energy. The only practical way to build it at the moment is with coal. Is there any coal nearby that could be used if the flasher waves failed?
Well, it's interesting because first of all, we wouldn't like to mine nearby. In fact, because mining gives rise to a lot of radio frequency interference. So if we were to do any mining nearby, that would almost destroy the signals that we saw. The largest renewable energy power stations in the world right now are of the order of a few tens of megawatts. I think there's one in Portugal with 2 megawatts. No, that's someone in the audience is better versed than would be in this. And in talking to our industry colleagues, they're confident that on the timescale that we're talking about when we get to the SPA, that 100 megawatts is practical. Particularly, what I didn't do in that 100 megawatt calculation was I didn't reduce the energy consumption due to some of the cooling, the passive cooling technologies that we're now investigating. So I think there's 2 routes. I think the route that renewable energy is going will get us there, but we also have to reduce the overall energy footprint as well. I think by coming at it from both angles, we'll be able to get there. But, you know, do I know for certain we'll be able to do any of this? And the answer is no. But I think that in that answer lies the innovation in order to get there.
You talk about the flat detectors that you mentioned in the middle of the how do they look? Are they phased array?
Yes, they are phased arrays. Essentially, what we do is we steer them electronically, so you can actually delay the reception of the radio waves as they travel through the system. In fact, Professor Richard Webster, sitting in the front row, is is involved in one of the US Australian experiments here. So what you can actually do is, although they don't move physically, you can actually point a beam on the sky in any particular direction. So they are simply phased arrays.
Why are they particularly low frequency?
Because the computational challenge around delaying these larger, higher frequencies is just sufficiently large that we even projecting for Moore's law, we can't build a computer sufficiently large in order to do phased array feeds at many gigahertz. And we might be able to do that. We might be able to afford to do that in about 2050. So the next version of the Square Kilometre Array might have all flat panels.
Good question is regarding serendipity. You mentioned the Large Hadron Collider led to the development of the internet and the web. There may be some spin-offs in this particular technology as well. It's hard to quantify that. But one obvious one would be the fact that you're putting in such a high-speed fibre optic network through remote parts of Australia. And as a consequence of that, you'll revolutionise the way that the mining industry operates in terms of remote mining. Have you given much thought and much collaboration with the mining industry with regard to this?
We're talking a lot with the mining industry, and particularly within the organisation I work for, CSIO, all that sort of tele-operational model. That's mining, that's also telehealth, because it brings the sort of opportunity to do virtual intensive care across these broad bandwidth links. So there's a whole slew of things that we can do, with this very large broadband infrastructure across the world. So are we talking to people? Absolutely. Are we talking as much as we'd like? No, because the trouble is, there's so many challenges in this that we tend to get focused onto actually building a telescope. What's my major concern at the moment? My major concern is to ensure that we have the native title permission to get on the site.
Up the back there.
I'm having trouble trying to understand how to get a pixel out of two separate telescopes.
Yeah, I said it's not quite right thinking about it in terms of pixels on the sky, but essentially, shall I take them into Fourier space and then back again? I'll see you later, okay?
Yes.
What about the logistics of actually servicing the equipment? You have to have a huge team of people, I presume, to do that. And of course, somebody else mentioned analysing an enormous amount of data. I mean, this would almost have an implication for the science communities right throughout the world. How do you train people up for that sort of task?
Yeah. Well, I think that we're taking our astronomical community through those sorts of data challenges. Things like the virtual observatory are being developed in terms of federating very large data sets in a number of different wavelength areas. And as we roll out Pathfinder telescopes like the Australian SK Pathfinder, we're trying to bring our communities up to speed. Remember, the SK will be used by global astronomers, so there's a large community out there, and a large community that's being stepped up. In terms of operations overall, the operational model will have to be a fly-in, fly-out model. It will also have to cope with a certain degree of redundancy amongst the antennas. So if something goes wrong in an antenna, you don't rush out to replace it straight away. There's 3,000 antennas, so you wait for a number to go down and then go and fix them on a weekly cycle. I mean, one of the differences between Australia and South Africa's configuration, of course, is around the areas of security. South Africa would probably have people drive to their telescopes, whereas in Australia probably people fly out to telescopes. When most of the telescopes, as I say, are within half of them within 5 kilometre by 5 kilometre region, and about 90% of them within 100 kilometres. So that's easily flyable to from one station. For the rest of the stations across Australia, we'll have to site those antenna stations, or we're planning to site those antenna stations where there exists existing infrastructure. So some of the ones you saw on the east coast are in places like Putney Park's Radio Telescope, places like Hobart and Seduna, where there exist existing facilities for people to support them on site. So yes, it's a huge challenge. I mean, that's where the 150 million euros per year operating comes into this, because of the number of people who would have supporting this. But there are ways to reduce it through a regular maintenance and response in something goes down.
Last question.
What's the decision-making process as to whether South Africa?
Well, that's such a good question.
And what do you do if you don't get it?
I think I'm probably the wrong person to ask what we do if we don't get it. I mean, I think people view it as, again, this is my own personal view. People talk about winning the SPA. I actually don't think that's a good articulation of it. Because frankly, in order for countries to invest in it, every country has to win from the SPA. And it's not just about putting a radio telescope